We proved that our initial model, when first launched by the init events, can establish the invariant conditions. Let's now try to do a similar reasoning to see whether or not these invariant conditions can be preserved by the ordinary events, I mean the non-init events. But luckily, we only have one event to really consider, which is the final events. We'll get there. All right, normal question, how many sequence is to be proved? It really depends on how many ordinary or non-init events we have multiplied by how many invariant conditions we have. So in this case, we have only one non-init event, which is the final event, just one. How many invariants do we have? We still have 4. So 1 times 4. So we got 4 invariants to consider. So this formula is really consistent with what we covered earlier in the bridge controller example. So we have 4 sequences generated for invariant preservation. Let's try to prove some of them together, and the remaining ones will be left to you as exercises, as usual. Let's take a look. So we are trying to prove about invariant preservation. What sequence do we need to formulate? Let's recall the rule for the proof obligation. For the hypotheses, we have to include the axiom, the invariant condition. You might be wondering, should it be abstract invariance or concrete invariance? If you're wondering about that, that means you have a little bit confusion over here. We are not talking about refinements. So there is no notion between abstract versus concrete. We're only talking about the initial model. So there's only invariance over here, not abstract, not concrete, just invariant. We're going to include the invariant in its pre-states in the hypothesis, and also the guard for the events. In this case, it will be just the final events, the guard over here. And also, this will be the invariance at the post-states should be satisfied with the effects of the events final apply. Of course, for that, we need to base on its before-after predicate, which I'll get into also when I do the formulation. Right, let's now try to do that. Let's now try to do the same invariance preservation. We do invariance 01A, this one here, and also we do invariance 02, which is this one over here. Right, let me just highlight them first. So the first one to do will be invariance 01A over here. And the second one that we want to do will be invariance 02. That's the one, right? Let's now try to do that. Hypothesis, we have to include the axiom, right? So you can see the axiom over here, in which case we're going to include all the axiom over here as before. And we also need to include all the invariants in their pre-state. Let's just put the axiom first. So we got n larger than 0, f a member of the set of partial functions, so sorry, the set of total function between the two sets, 1 to n as the interval set, total function d, and also Boolean equals the two member true and false. To make sure I spelled it correctly. Right, so these are the axiom. And then we need to include the abstract, yes, not the abstract, just the invariants. Just be careful. Just the invariant in the pre-states. Right, we're going to include all the invariant condition over here. All of them. So, which will be G, a member of the partial function between 1 to n, partial function D. And also B is a member of Boolean. And also B equals false, implies G equals empty set. Finally, true, B equals true. B equals true implies G equals F. And let me just make this smaller so I can have more space. Okay, let's make it smaller. Okay, that's good. And what else? We also need to put in the guard for the events, right? And the guard will be over here for the final events. B equals false. And we need to have the turnstile over here. Turnstile. And what should this be? Okay, I'll put a star over here. And the star over here should be, since we are talking about invariance 01A, this invariant here, but we need to put the variables into prime to indicate their post-state value, which is something we did just earlier for the invariant establishment. Let me just go there directly. So G prime is a member of 1 dot dot and partial function D. And we need to see what the before after predicate is for the final events. Let's take a look. Before after predicate here should be G prime equals F, and also B prime equals false. And what should we replace? We should really replace G prime over here by F. And that's it. That's the only variable that appears in this expression over here. So overall, we're going to need this particular goal. It will be F, a member of the set of partial functions between 1 to n, and also D. Right, so that's about the sequence. You can also look at the slide too for the more like a better layout version. But it's really important to see how to derive it. Let's also do the second one very quickly. And the hypothesis is going to mostly identical, except, well, actually it's going to be identical since we are talking about the same events. So the guard over here will be the same. We don't have multiple events to consider, just one. So the hypothesis will be exactly identical. Let me just copy that just to save some writing. So I'm going to put it over here. And what's really left is about the goal to really put in. Right? Let me put star, star over here. And the invariant that we need to put in will be invariant 02. So what I'll do is I'm going to put B prime, which is a Boolean variable, equals true, the post-state evaluation for that implies G prime equals F. And let me emphasize again, the reason that we don't really put prime for F is because F was declared as a constant. Constant really don't have the notions between pre and post states, right? And what's going to be the replacement? Let's try that. B prime over here is going to be replaced by false. And G prime over here is going to be replaced by F. So what we end up having as the goal would be false equals false implies F equals F. And again, you can see the better layout version on the slides. But again, I'm just trying to show to you the derivation process. So these are the two sequences generated related to invariant preservation. It would be your exercise to generate the other sequence as practices. Let's now try to prove these two sequences. Right? And I'm just going to prove this one over here and also this one over here. So these are the two we formulated, and these two over here will be your exercises. Okay, let's see the first one. And this one here, we in this case, unlike the case for invariant establishment, in which case we may not need any of the hypotheses. But for this one here, I think we'll need it because we simply say F is a member of this. But the problem is we don't really know what exactly F is, so we might need to use some of the hypotheses, right? So what hypothesis can we really use? Well, I can see this one here looks quite promising. It has almost the same form as this. However, you got to be very careful. You can see here we got, given that it is a total function, can we use that to prove that it is a partial function? Formally speaking, if I know it is a total function, does it imply it is a partial function? It turns out it is. However, the other way around is not the case. So imagine hypothetically, if we say it is a partial function over here, and we want to prove that it is a total function, then it cannot be proved, right? So guys, you want to make sure you refer to lecture number 1 about the math review to see why a total function is a partial function. However, the other way around is not true, meaning that a partial function is not a total function always. Let me write down the proof. So what I will do is I'm going to just do the monotonicity first of all to drop all the irrelevant hypotheses. I'm only going to keep this one here so we can be much more focused. So I'm going to get F, a member of the set of total function between 1 and n, and D. Turnstile, the goal will be F, a member of the set of partial function over here, D. Right? That's why it's so important, which I mentioned in the earlier slide, you have to review what we covered earlier about a review, math review. Right, let's now box it over here. Okay, and this one here, I believe we can actually say by arithmetic we can prove it, because given that it is a total function, we know that it is always a partial function. Okay, so by arithmetic, now it's proved. You may actually want to put some extra justification over here, right? This one over here. And what I can put is, I would say, number one, a total function is a special case of partial function where the domain simply occupies the entire left set. Right? That's something. I think that's enough, right, for number one. But you just remember what I just mentioned. I think that's something you want to review as well. Number two, I can also just say to show my understanding. But a partial function is not necessarily a total function. I think if you actually put these two justifications, it would be very clear to the grader that you actually understood about why you can apply the arithmetic. Total function is a special case of partial function, but a partial function is not necessarily a total function. Let's now move on to the next sequence proof, this one over here. Right? So this one over here, I would say that one there would be kind of like a special case where we don't need any of the hypothesis. Why? Because when I look at this over here, we know that true equals false should be false. And then false implies anything, in which case we're going to get true as the goal. In that case, we can actually conclude by true R as the axiom inference rule, right? Let's now do that. Of course, you know, again, the point is, you don't necessarily be lucky always not to use any of the hypotheses. You have to judge by yourself. Right? So for this one here, we can say by monotonicity, first of all, I can drop all the hypotheses. None of them will be useful for me. Turnstile, I would say true equals false implies F equals empty. That'll be the first one I want to write. Okay, and let me just make it smaller. I think I still need some space. Okay, I think that's still readable. Okay, and by arithmetic, which I'm going to justify further in just a moment, by arithmetic, you know what, I think we put it here. Let's say by arithmetic, what we will get is this. Turnstile, we just get true. And I'm going to explain with additional details why we can reduce this to be true. Okay, you can think about this one is going to follow the arithmetic. And finally, since we got a goal being true, so we can actually say true appearing to the right of the turnstile. So it's now proved. Let's now try to further justify this arithmetic step over here. Okay, over here. Okay, let me put it here. Number one, we can say true equals false is equivalent to false. Think about this is one member value from the Boolean. Another member from the Boolean carry a set. Of course, there are different members. Of course, the equality between them should be equivalent to the predicate false. And number two, we know that false implies P is always equivalent to true, right? That's so-called a zero of implication, right? So these are the two justification you want to make sure you actually write down, you know, to show your understanding as well. Right, so these are the two sequences I want to go over with you for their proofs. And for these two, you want to make sure, number one, to practice formulating them, and number two, to practice proving them. And I think for the initial model, all the proofs that will be needed will be quite straightforward. Right, and we are done with proving the invariant preservation aspect for the model. And of course, these are the 4 sequences ultimately, and make sure you complete the exercises. Let's now draw the quick conclusion about the initial model, a summary. So for the initial model, we can claim that it's provably correct, given that we already proved about establishment of the invariance, preservation of the invariance, and also the deadlock freedom is something I will leave to you as exercise. Think about how you may actually specify the deadlock freedom. I'll leave that to you. You can definitely refer to maybe the initial model for the bridge controller to see how we formulated the proof and prove it. I think this one should be rather straightforward. I'll leave that to you. And this is simply just a summary. I think everything's straightforward, so we don't need to spend any extra time going over that. However, if you refer to the notes, I still make the page clean over here for you as a reference. And just remember, for the initial model without any refinements, you have to make sure you prove about these 3 aspects. All right, and we'll move on to the first refinements for our FTP system.